Have you ever looked up at the stars and felt that whisper of mystery, that tug of something far older and wiser than ourselves? The night sky is more than just a scattering of distant lights. It's a living archive, a cosmic ledger where the universe has etched its deepest secrets. And here's the astonishing truth: some of those secrets weren't just written in the last few million years. They were crafted by ancient celestial events so powerful, so transformative, that their echoes still shape the cosmos today. These are the forgotten architects of the universe, stellar phenomena so colossal they've been hiding in plain sight, quietly rewriting the rules of astronomy without us even realizing it. Think of it like uncovering an ancient city buried beneath a modern metropolis. For generations we've walked the streets of our understanding, unaware of the foundations beneath our feet. But now, thanks to breakthroughs in technology and a fresh wave of curiosity, scientists are peeling back those layers. They're finding supernovae that exploded when Earth was young, quasars that lit up the early universe like beacons, and cosmic collisions so violent they sculpted the galaxies we see today. These aren't just relics of the past, they're active blueprints, still guiding how stars form, how black holes grow, even how the fabric of space itself bends and twists. So what happens when we finally listen to these celestial storytellers? Everything changes. The universe isn't just expanding, it's remembering. And as we piece together these fragments of cosmic history, we're not just solving puzzles about the distant past. We're uncovering clues about our own future, about the fate of galaxies, even the ultimate destiny of light itself. This isn't just astronomy, it's archaeology on the grandest scale imaginable. And by the end of this journey, you won't just see the night sky differently, you'll feel it like a conversation across billions of years, waiting patiently for us to finally understand. Long before galaxies spiraled into existence, before planets found their orbits, the universe was a blank canvas waiting for its first brushstrokes of light. And the artists, they were population 3 stars, celestial titans unlike anything we see today. Imagine stars so massive they could make our sun look like a pebble beside a mountain. Born from nothing but hydrogen and helium in the wake of the Big Bang, these were the universe's first furnaces, burning ferociously bright and dying young in explosions so powerful they lit up the darkness of the early cosmos. But here's what makes them truly extraordinary: when these stars died, they didn't just fade away, they became cosmic alchemists, forging the first heavy elements in their cores: carbon, oxygen, even the iron in your blood, and scattering them across the void like seeds. Without population 3 stars, the universe would still be a vast, empty soup of simple atoms. No planets, no life, just endless hydrogen drifting in the dark. Yet for all their importance, we've never directly seen one. These stars lived fast and died billions of years ago, leaving behind only faint chemical fingerprints in the light of their descendants. It's like trying to reconstruct a lost language from a handful of scattered words. But astronomers are getting closer. By studying the oldest stars in our galaxy, the faint, ancient survivors that formed from the ashes of those first giants, we're piecing together clues about their vanished parents. And what we're finding is rewriting the story of how everything began. Take the star known as He-152391, for example, found lurking in the outskirts of the Milky Way. It's one of the most metal-poor stars ever discovered, a term astronomers use to describe stars with almost no heavy elements. That scarcity is a direct inheritance from the population 3 era. Its composition is a time capsule, preserving the pristine chemistry of a universe still in its infancy. Every flicker of its light carries whispers from a time when the cosmos was taking its first, fragile steps toward complexity, and that's just the beginning. Hidden in the glow of these ancient survivors are clues about the very nature of the first stars, how they formed, how they shaped the galaxies that followed, even how they might have ignited the supermassive black holes that lurk at the hearts of galaxies today. Population 3 stars didn't just light up the universe, they built its scaffolding, set its rules, and handed down the ingredients for everything that came after. We're only now starting to understand how much we owe to these forgotten giants. The death of a population 3 star wasn't just an ending, it was a cosmic rebirth. When these primordial giants reached the end of their brief, brilliant lives, they didn't fade quietly, they detonated with unimaginable violence, tearing themselves apart in supernovae so powerful they could outshine entire galaxies. But these explosions weren't merely destructive, they were transformative, scattering newly forged elements across the void like celestial breadcrumbs. For the first time in history, the universe held more than just hydrogen and helium. Traces of carbon, oxygen, silicon, and iron now drifted through space, the raw materials for everything that would follow. This was the moment the cosmos grew up. Before these stellar deaths, the universe was like a vast, empty kitchen with only 2 ingredients. Those first supernovae were the cosmic equivalent of discovering fire suddenly. Complexity became possible. Gas clouds enriched by these explosions could cool faster, clump together more easily, and give birth to a whole new generation of smaller, longer-lived stars. Stars like our own Sun, which would eventually form planets rich with the very elements those first stars created. We're not just observers of this story, we're products of it. Every atom in your body that isn't hydrogen was forged in the heart of a dying star, either from that initial population, 3 generation, or their descendants. Yet the impact didn't stop there. Some theorists believe these supernovae might have been 1,000 times more energetic than anything we see today. When stars that massive collapse, they don't just explode, they might collapse directly into black holes, seeding the early universe with the gravitational anchors around which galaxies would later form. Imagine a single stellar death so titanic, it planted the seed for a future galaxy like our Milky Way. That's the scale of influence these ancient architects wielded. And now, after billions of years, we're finally catching glimpses of their legacy. The James Webb Space Telescope isn't just looking for the stars themselves, it's hunting for their ghostly afterimages in the chemical makeup of the earliest galaxies. Like detectives analyzing ashes at an ancient fire site, astronomers study the ratios of elements in these distant systems to reverse engineer the properties of the stars that must have existed before them. Recent observations of unexpectedly bright infant galaxies may hint at the presence of population, 3 stars burning in their cores, their intense ultraviolet radiation lighting up surrounding gas like cosmic lighthouses. But perhaps the most tantalizing clue comes from the cosmic microwave background, the afterglow of the Big Bang itself. Tiny fluctuations in this ancient light might carry imprints of those first supernovae, like ripples from stones thrown into the universe's earliest pond. If we can decode those faint signals, we might finally hear the echoes of the explosions that set the stage for everything we know. What's astonishing is how much these long-dead stars still shape our cosmic neighborhood. The distribution of galaxies, the chemistry of stars, even the very structure of space-time, all bear fingerprints of that first generation. They didn't just light up the darkness. They built the universe's operating system, writing the rules that every subsequent star and galaxy would follow. And as we piece together their story, we're not just uncovering ancient history. We're learning the universal laws that will govern the cosmos for billions of years to come. So the next time you look up at the night sky, remember, you're not just seeing stars. You're seeing the children of giants, the living legacy of those first magnificent architects, and somewhere out there in the darkness, the light of their creation still travels, carrying stories from the dawn of time itself. Hypernova make ordinary supernova look like firecrackers in comparison. Picture a detonation so fierce, it unleashes more energy in seconds than our Sun will produce in its entire 10 billion-year lifetime. These weren't just stellar deaths, they were cosmic cataclysms, the final screams of the universe's first true giants, when a population 3-star, hundreds of times more massive than our Sun, reached the end of its fleeting existence. It didn't just collapse, it imploded with such ferocity that it became a hypernova. The shockwaves from these explosions didn't merely ripple through space, they carved tunnels through the fabric of the early universe, leaving behind fingerprints we can still detect today. What made hypernova so transformative? It wasn't just their raw power, it was their alchemy. Deep in the cores of these dying behemoths, conditions became so extreme that atoms were forged into elements heavier than anything the universe had ever seen. Gold, platinum, even uranium, the very materials that would one day form planets and power civilizations, were born in these violent final moments. When the hypernova erupted, it blasted these newly minted elements across thousands of light years, enriching entire galaxies with the seeds of future chemistry. Without these explosions, the periodic table would be a shadow of what it is today, but hypernova did something even more profound: they shaped space itself. The gamma-ray bursts produced in these events, some of the brightest electromagnetic phenomena known, acted like cosmic lighthouses, beams of energy so intense they could outshine 1,000,000 galaxies for a few terrifying seconds shot across the universe. Astronomers now use these bursts as guideposts, glimpsing the conditions of the early cosmos by studying their afterglows billions of years later. And here's the twist: those same beams might have jump-started star formation in distant gas clouds, their radiation compressing nebulae until they collapsed into new stellar nurseries. One star's death became another's cradle. The aftershocks didn't stop there. Recent supercomputer simulations reveal hypernova may have played a surprising role in sculpting the universe's large-scale structure. Their explosive energy could have created vast bubbles in the intergalactic medium, pushing matter into the filaments and voids we observe in modern galaxy surveys. Think of it like tossing boulders into a still pond. The ripples rearranged everything in their path. Even now, the gravitational echoes of those ancient explosions might subtly influence how galaxies cluster together. Yet the most haunting legacy of hypernova lies in their silence. Most of these titans died billions of years ago, their light long since faded into the cosmic background. But their fingerprints are everywhere: in the gold in your jewelry, the uranium powering reactors, even the calcium in your bones. We're literally made from the ashes of these celestial detonations. And as astronomers peer deeper into the past with tools like the James Webb Space Telescope, they're uncovering hypernova remnants hidden in the spectra of the universe's oldest stars, chemical ghosts, whispering secrets about how the cosmos built itself from chaos. Now, as we shift our gaze from these titanic explosions to the enigmatic quasars, remember, hypernova weren't just destroyers. They were the universe's first great chemists, architects, and storytellers. And their tale is still being written in the stars above us. Quasars are like the universe's first great light switches, flickering on in an era when everything was cloaked in darkness. Picture a single object so luminous it outshines the combined light of every star in its home galaxy, a supermassive black hole, millions to billions of times heavier than our Sun, devouring matter at a ferocious rate. As gas spirals into these cosmic monsters, friction heats it to millions of degrees, transforming the black hole's vicinity into the brightest continuous beacon in existence. These are quasars, and in the early universe, they didn't just illuminate the cosmos, they fundamentally changed it. Around 500 million years after the Big Bang, the universe was a fog of neutral hydrogen, a featureless void where light couldn't travel far without being absorbed. Then quasars erupted into existence, their blistering ultraviolet radiation stripping electrons from hydrogen atoms in a process called reionization. This was the moment the cosmos became transparent, like lifting a cosmic veil, Without quasars, the universe might have remained a shadowy realm, its light perpetually trapped. Their radiation didn't just clear the fog, it set the stage for every galaxy, star, and planet that followed, but quasars left more than just light in their wake. Their relativistic jets, narrow beams of plasma traveling near light speed, carved colossal bubbles in the intergalactic medium, shoving matter aside like cosmic bulldozers. Today we see the remnants of these bubbles in the large-scale structure of the universe, vast voids surrounded by filaments of galaxies, a fossil record of quasar activity from billions of years ago. Some astronomers even speculate these jets could have triggered star formation in distant gas clouds, their shock waves compressing material until it collapsed into stellar nurseries. One quasar's destruction might have seeded another galaxy's birth. What's truly baffling is how these supermassive black holes grew so big so quickly. The quasar nicknamed JWST-1026, for example, weighs in at nearly 2 billion solar masses, yet it existed when the universe was less than 700 million years old. That's like finding a skyscraper in the middle of an ancient wilderness where only huts should exist. How did these black holes accumulate such staggering mass in so little time? Some theories suggest they sprang from the direct collapse of primordial gas clouds, bypassing the star stage entirely. Others propose they grew from mergers of smaller black holes left behind by population-3 stars. Modern sky surveys have cataloged over 1 million quasars, each one a time capsule from a different cosmic epoch. The Sloan Digital Sky Survey alone has mapped their distribution across billions of light years, revealing how their numbers peaked around 10 billion years ago, a golden age of quasar activity. Today, most supermassive black holes are dormant, their fuel exhausted, but their light still travels toward us, carrying encoded details about the conditions of the early universe. Perhaps the most tantalizing clue quasars offer lies in their shadows. When their light passes through intergalactic hydrogen clouds, specific wavelengths get absorbed, creating a barcode-like pattern in the quasar's spectrum. These absorption lines are like tree rings, chronicling the density and chemistry of the universe at different eras. Some reveal vast reservoirs of water vapor in early galaxies, others hint at the existence of entirely unknown states of matter. Quasars aren't just relics, they're active participants in cosmic evolution. Even now, their radiation continues to shape galaxy clusters, heat interstellar gas, and influence the birth rates of stars. They're the universe's original architects, their light a bridge between the distant past and our present, and as we decode their messages, we're not just learning about black holes. We're reading the diary of the cosmos itself, written in photons older than Earth. Now, as we turn our attention to the shadows quasars cast, we encounter an even deeper mystery, the possibility of black holes that predate stars themselves, lurking in the darkness since the dawn of time. Primordial black holes aren't just another cosmic mystery, they're potential time travelers from the universe's first moments. While most black holes form from collapsing stars, these enigmatic objects might have emerged in the chaos just seconds after the Big Bang, when space itself was seething with unimaginable density. Picture quantum fluctuations so intense that pockets of space-time collapsed under their own gravity, birthing black holes before the first stars even flickered to life. Unlike their stellar counterparts, primordial black holes could be virtually any size from smaller than an atom to larger than a solar system. Their very existence would mean our cosmos was built not just on visible matter, but on invisible gravitational anchors woven into the fabric of reality from the beginning. What makes primordial black holes so revolutionary isn't just their origin, it's what they might explain. Take dark matter, for example. For decades, scientists have known that galaxies move as if they contain far more mass than we can see. Primordial black holes could solve that puzzle. If enough of them formed in the early universe, their collective gravity might account for the missing mass that binds galaxies together. Some theories suggest trillions of these invisible objects could be drifting through our galaxy right now, their subtle gravitational tugs the only hint of their presence. Detecting them pushes our technology to the limit. Astronomers hunt for telltale flashes when a primordial black hole passes between us and a distant star, bending light in a phenomenon called microlensing. Others listen for the faint hiss of Hawking radiation, the theoretical evaporation of small black holes predicted to emit particles as they slowly dissolve. The absence of conclusive detection so far only deepens the mystery. Are they too small, too rare, or simply hiding in regions we haven't probed? The implications stretch beyond dark matter. If primordial black holes exist, they may have served as seeds for the supermassive black holes we see at galactic centers today. A modest primordial black hole could have grown over billions of years, feasting on gas and merging with others to become the monsters powering quasars. This would rewrite the timeline of cosmic evolution, suggesting supermassive black holes didn't emerge from stars at all. They were there from nearly the beginning, sculpting galaxies around themselves like invisible potters shaping clay. Even their absence would speak volumes. Failing to find primordial black holes after extensive searches might mean the early universe was smoother than we thought, with no ultra-dense regions collapsing into black holes. That answer would force us to reconsider fundamental aspects of cosmic inflation, the rapid expansion moments after the Big Bang. Whether they exist or not, the hunt for these relics is teaching us about the universe's most extreme conditions. Now consider the web they might have woven. If primordial black holes clustered in specific patterns, their gravity could have guided the flow of matter in the early cosmos, determining where galaxies would eventually form. The cosmic web, that vast network of filaments and voids spanning the universe, might bear their fingerprints, a hidden architecture built by ghosts. Every time we map the large-scale structure of the cosmos, we're potentially reading a message left by these ancient gravitational architects. The deeper we look, the clearer it becomes. The universe's history isn't just written in starlight, it's etched in the invisible, the hypothetical, the nearly forgotten. The story is far from over. The cosmic web is more than just the universe's largest structure, it's the ultimate architectural blueprint, the grand design left behind by those ancient stellar architects. Imagine a tapestry woven from filaments of galaxies, gas, and dark matter, stretching across billions of light years in a delicate, interconnected dance. These aren't random patterns. Every thread, every void, every cluster tells a story shaped by the violent births and deaths of the first stars, the searing radiation of quasars, and the invisible pull of dark matter. To understand how this web formed, picture the early universe not as a smooth soup of matter but as a simmering cauldron of tiny fluctuations. Gravity amplified those faint ripples over time, drawing matter into dense knots connected by tendrils of gas, like water pooling in the grooves of a wrinkled sheet. But gravity didn't work alone. Hypernovae and quasars added their voices to the chorus, their explosions and jets carving bubbles in the cosmic foam, pushing matter into walls and leaving behind vast, empty voids. The heaviest elements forged in those stellar furnaces then flowed along these filaments, enriching future galaxies with the ingredients for planets and life. Modern telescopes like Euclid and the James Webb Space Telescope are now mapping this web in unprecedented detail, capturing the faint glow of intergalactic hydrogen illuminated by ancient starlight. What they reveal is astonishing. Galaxies aren't scattered randomly, they're perched along these invisible highways, strung like pearls on cosmic strings. Even more remarkable, the web structure matches supercomputer simulations of dark matter's gravitational influence, proof that the universe's hidden skeleton guides everything we see. But the cosmic web isn't just a relic, It's still evolving, still growing. Collisions between galaxy clusters send shockwaves rippling through the filaments, while supermassive black holes pump energy into the voids. Every new observation peels back another layer, showing us how the universe builds itself, how chaos becomes order, how explosions become bridges, and somewhere in that vast network, the echoes of those first architects still resonate, their handiwork written in the stars. Now consider this: if we could step back far enough, we'd see that even our Milky Way is just a single stitch in this cosmic quilt, woven into place by forces older than time. Every galaxy, every nebula, every planet exists because that web held them, because those ancient stellar phenomena laid the foundation for everything that followed. The cosmic web isn't just the universe's past, it's its living, breathing present and its future. That story is still being written. Galaxies are more than just collections of stars, they're living museums, each one a palimpsest where the universe has layered its history over billions of years. The Milky Way didn't spring into existence fully formed. Like a city built atop ancient ruins, it grew incrementally, its spiral arms and central bulge shaped by forces we're only beginning to understand. And the architects, they were the very first stars, those population 3 behemoths whose death seeded the cosmos with the heavy elements that would later coalesce into generations of smaller, longer-lived stars. Without their explosive farewells, galaxies as we know them simply couldn't exist. Take dwarf galaxies, for example. These faint, sprawling clusters are the universe's time capsules, relics of an era when gravity was still stitching matter together. Unlike massive spiral galaxies, many dwarfs have barely changed since their formation. Their stars are ancient, their metal content astonishingly low, direct descendants of that first generation of stellar pioneers. By studying them, astronomers have uncovered something surprising. The earliest galaxies might not have formed gradually but in sudden bursts, triggered by the shockwaves of nearby hypernova. Imagine a cosmic domino effect where one star's death sparks the birth of thousands more, yet construction wasn't a peaceful process. Quasars played the role of cosmic regulators, their blistering radiation and powerful jets acting like galactic sculptors. When these active black holes switched on, their energy could heat surrounding gas so intensely that star formation ground to a halt in their vicinity, a phenomenon called feedback. It's as if the universe had its own thermostat, balancing growth and restraint. Some galaxies grew massive, others remained small, their development stunted by these celestial overseers. The Milky Way's current size and structure, that's the result of billions of years of negotiation between gravity's pull and quasar-driven pushback. Then there's dark matter, the invisible scaffolding that determined where galaxies would rise. Though it neither emits nor reflects light, its gravitational influence is undeniable. Without dark matter's subtle tug, ordinary matter would have dispersed too thinly to collapse into galaxies at all. Modern simulations reveal a stunning dance. Dark matter forms vast halos first, and gas follows, flowing into these gravitational wells where it cools, condenses, and eventually ignites into stars. The largest galaxies, like our own, likely grew through mergers, violent collisions with smaller neighbors that sent stars carrying into new orbits, reshaping entire structures over eons. The proof is written in the stars themselves. Astronomers can read a star's composition like a birth certificate, revealing not just its age but the conditions of its formation. Metal-poor stars in the Milky Way's outer halo are immigrants, likely captured from dwarf galaxies devoured long ago. Their trajectories across the sky trace the ghostly outlines of these ancient mergers. Meanwhile, stars nearer the galactic center tend to be richer in metals, forged from gas enriched by countless supernovae over generations. Each stellar population is a chapter in the Milky Way's autobiography. What's astonishing is how dynamic this process remains. Even now, our galaxy is digesting the Sagittarius dwarf spheroidal, a tiny neighbor it's been tearing apart for billions of years. And in 4 billion years, the Milky Way will collide with the Andromeda Galaxy, an event that will rewrite both galaxies' structures entirely, yet none of this chaos is random. It's the continuation of a blueprint drafted by those first stellar architects, their explosions, their chemistry, even their silence echoing across the ages. So when we gaze at the night sky, we're not just seeing stars, we're seeing the aftermath of cosmic construction zones, the work of countless generations of celestial builders. And the blueprint they left behind, it's still unfolding, one stellar birth, one galactic merger at a time. The oldest stars in the Milky Way aren't just twinkling relics, they're celestial detectives, holding evidence of the universe's first cataclysms. Nestled in globular clusters like M4 and Omega Centauri, these ancient suns burn with compositions so pristine they're practically time machines. Unlike younger stars polluted by generations of supernova debris, their atmospheres carry undiluted signatures of the cosmos's raw ingredients. When astronomers analyze their light, they're not just studying stars, they're decoding the aftermath of population, 3 explosions from an era before galaxies took shape. One of the most telling clues lies in the odd chemistry of stars like 814023. This galactic elder, over 13 billion years old, contains trace amounts of elements like strontium and barium, materials typically forged in neutron star collisions. But here's the puzzle: neutron stars take time to form and merge, longer than this star's age should allow. The solution: its heavy elements might have been scattered by hypernova from the first stellar generation, detonating with such force they skipped intermediate steps in cosmic nucleosynthesis. These stars aren't just old, they're witnesses to a vanished era of unimaginable violence. Then there's the galactic halo, a vast spherical shell of stars surrounding the Milky Way's disk. Unlike the orderly spiral arms, this region is chaos incarnate: stars orbiting at wild angles, some even moving backward. This isn't random turbulence, it's the graffiti left by ancient mergers. Billions of years ago, dwarf galaxies like Gaia and Enceladus collided with our young Milky Way, their stars splashed across the halo like paint flung onto a canvas. But what orchestrated these collisions? Primordial black holes could be the missing architects. If these ancient gravitational traps lurked in early dwarf galaxies, their invisible pull might have steered them into mergers that shaped our galaxy's growth. At the Milky Way's heart lies another enigma, Sagittarius A, our supermassive black hole. While it's relatively quiet today, its origins are anything but ordinary. Most galaxies host black holes proportional to their size, yet Sagittarius A is oddly lightweight for a galaxy like ours, a clue it might have formed differently. Instead of growing slowly by swallowing gas, it could have started as a primordial black hole or the remnant of a direct collapse giant from the universe's first 100 million years. Recent observations of stars orbiting perilously close to it reveal another surprise. Their path suggests Sagittarius A might not be alone. Smaller black holes could swarm around it like bees around a hive, remnants of ancient mergers or even captured primordial objects. Modern telescopes are turning these hints into revelations. The Gaia spacecraft maps stellar motions with unprecedented precision, tracing the Milky Way's growth through the trajectories of its oldest stars. Meanwhile, spectrographs like those on the Very Large Telescope dissect starlight to uncover elemental abundances, reading the chemical diaries of the cosmos's youth. Even gravitational wave detectors join the hunt, listening for the echoes of black hole mergers that might reveal primordial origins. Each dataset is another brushstroke in a portrait of our galaxy's hidden past, a past written in the language of hypernova debris, dwarf galaxy collisions, and black holes older than starlight. So when you gaze at the Milky Way's shimmering band across the night sky, remember, you're not just seeing stars, you're seeing the aftermath of cosmic construction projects, the fingerprints of architects who worked in darkness billions of years ago. Their blueprints are still unfolding, their secrets waiting in the glow of ancient suns, and with every new discovery, we're not just learning about our place in the universe, we're meeting the ghosts who built it. We're witnessing a golden age of cosmic archaeology, where cutting-edge tools act as time machines, peeling back layers of the universe's history with unprecedented clarity. The James Webb Space Telescope isn't just observing distant galaxies, it's capturing starlight that left its source when the cosmos was barely 5% of its current age. Recently, JWST stunned astronomers by spotting a quasar from just 700 million years after the Big Bang, its light revealing chemical signatures that suggest it's already surrounded by mature stars. How could stellar populations have aged so quickly? The answer might lie in population, 3 stars that lived and died in cosmic blink, seeding the universe with heavy elements far earlier than models predicted. Meanwhile, the Atacama Large Millimeter Array in Chile offers a different perspective, seeing not invisible light, but in the faint radio whispers of molecules. ULMA detection of carbon monoxide in galaxies dating back 12 billion years provides smoking gun evidence for hypernova enrichment. These molecules shouldn't exist in such ancient systems unless massive first-generation stars had already scattered their ashes across the cosmos. The real surprise came when ULMA mapped these molecular clouds in 3 dimensions, revealing structures strikingly similar to modern stellar nurseries, proof that the universe figured out efficient star formation recipes astonishingly early. But some architects leave no light signatures at all. That's where LIGO gravitational wave detectors come in, listening for the space-time ripples from black hole mergers. In 2015, LIGO made history by detecting its first collision, but the real excitement came with subsequent observations of surprisingly massive mergers in pairs totaling over 100 solar masses. Could these be primordial black holes, dating back to the universe's infancy, or perhaps the remains of population, 3 stars that collapsed without supernova? Each new detection adds pieces to the puzzle, with some events originating from regions devoid of visible galaxies hinting at invisible, ancient structures lurking in the darkness. Supercomputers like NASA Pleiades and Japan's Fugaku weave these disparate clues into coherent narratives, running simulations that model everything from quark-gluon plasma in the first microseconds to galaxy cluster formation over billions of years. They test wild scenarios that telescopes can't observe directly. One groundbreaking simulation suggested primordial black holes could explain not just dark matter, but also the unexpected heft of early supermassive black holes, by serving as ready-made seeds that grew exponentially through mergers. Another recreated how hypernova shockwaves might have triggered synchronized star formation across vast cosmic distances, explaining why some ancient galaxies appear suspiciously mature. Perhaps the most democratic tool in this cosmic detective work is citizen science. Projects like Zooniverse's Galaxy Zoo enlist hundreds of thousands of volunteers to classify unusual objects in telescope images. In 2007, amateur participants discovered an entirely new class of galaxy green piezo-compact systems undergoing furious star formation that resemble conditions in the early universe. More recently, volunteers helped identify rare, dark galaxies that emit almost no starlight, potentially revealing how primordial gas clouds first began collapsing. These discoveries prove that cosmic archaeology isn't just for professional astronomers. The universe's history belongs to anyone willing to look. Together, these technologies form an interdisciplinary toolkit that's challenging long-held assumptions. The standard model of cosmology never predicted quasars existing so early, or galaxies appearing fully formed when the universe was in its infancy. Some observations even hint at possible gravity anomalies, that could suggest modifications to Einstein's theory on cosmic scales. Each anomaly is a gift, an opportunity to refine our understanding of those ancient architects whose handiwork still shapes everything we see, the most exciting realization. We've barely scratched the surface of their legacy. The universe's instruction manual might need a rewrite, because what we're discovering now doesn't just add footnotes to cosmology's grand narrative, it tears whole chapters out. Take dark matter. For decades, we've treated it as an invisible, passive glue holding galaxies together, but if primordial black holes really do lurk in the darkness, everything changes. These ancient gravitational traps could be more than just dark matter candidates. They might be its architects, sculpting the cosmic web through sheer gravitational influence while remaining nearly undetectable. Suddenly, dark matter isn't just a placeholder in equations, it's a dynamic player with a backstory stretching back to the universe's first second. Then there's nucleosynthesis, the sacred recipe for how elements formed. Standard models paint a tidy picture of gradual enrichment through supernova, but hypernova toss that script aside. Their explosions were so violent, they could have forged elements like gold and uranium in seconds way ahead of schedule. When astronomers find these heavy metals in stars barely younger than the Big Bang itself, it's like uncovering a Renaissance painting in a prehistoric cave. The universe's chemical evolution wasn't linear, it was a riot of creativity, with hypernova as its reckless, brilliant artists. Quasars deepen the mystery. These luminous behemoths weren't supposed to exist when the universe was only 5% of its current age. According to textbooks, supermassive black holes need billions of years to grow, yet there they are, shining impossibly bright in the cosmic dawn. One theory suggests they skipped the stellar phase entirely, collapsing directly from primordial gas clouds. Another posits that population 3 stars left behind black hole seeds so massive they ballooned into quasars almost overnight. Either way, their existence forces us to confront an uncomfortable truth: the early universe didn't play by our rules. Even the cosmic microwave background, the so-called baby picture of the universe, harbors anomalies. Tiny temperature fluctuations in this ancient light don't match predictions perfectly. Some regions are colder, others hotter, as if something stirred the primordial soup before it cooled. Could those irregularities be scars from hypernova shockwaves, imprints of primordial black holes colliding, or evidence of physics we haven't discovered yet? The answers might rewrite not just galaxy formation, but the very timeline of the Big Bang, which brings us to the darkest architects of all, dark stars. Not the twinkling specks we see tonight, but hypothetical monsters powered by annihilating dark matter, not nuclear fusion. These would be stars unlike any other, vast, cool, and glowing faintly with the energy of particles we've never seen. If they existed in the early universe, they could explain why some pockets of space heated up faster than models predict, and when they finally collapsed, they might have birthed the very black holes that later became quasars. Dark stars remain theoretical for now, but their potential to upend cosmology is very real. After all, in a universe where the impossible keeps becoming reality, why shouldn't stars made of shadow light the way? The lesson here isn't just that we've gotten things wrong, it's that the cosmos is more imaginative than we ever dreamed. Every time we think we've uncovered its rules, the universe whispers back with relics that defy explanation. And the most thrilling part, the next revelation might be hiding in plain sight, written in the light of a star, the echo of a collision, or the silence of the dark between galaxies. Dark stars weren't just stars, they were cosmic anomalies, celestial paradoxes glowing with a light no telescope had ever seen. Picture a behemoth 1,000,000 times more massive than our sun, yet eerily cool, its surface barely warmer than a summer's day. Unlike ordinary stars that burn hydrogen in their cores, these hypothetical giants drew energy from something far stranger, the annihilation of dark matter. As invisible particles collided and destroyed each other deep inside, they released energy that kept the star puffed up and luminous for millions of years. The result? A colossal, diffuse object unlike anything in the modern universe, one that could rewrite the entire timeline of cosmic dawn. Recent James Webb Space Telescope observations might have already glimpsed their fingerprints. Some of the earliest galaxies JWST has spotted shine far brighter than models predict, packed with mature stars that shouldn't have had time to form. Dark stars offer a tantalizing solution. If these exotic objects lit up the early universe, their intense infrared glow could explain the anomaly. Even more intriguing, their eventual collapse might have jump-started supermassive black holes, bypassing the need for slower growth from stellar remnants. Imagine a dark star finally exhausting its dark matter fuel, imploding directly into a black hole hundreds of thousands of times the Sun's mass. That single cataclysm could plant the seed for a future quasar, solving the riddle of how supermassive black holes grew so big so fast. Yet the implications go deeper than black holes. Dark stars would mean dark matter isn't just an invisible bystander, it was an active participant in cosmic evolution. Their existence suggests dark matter particles can collide and annihilate, a property that would help explain why we haven't detected them directly in underground labs. If dark matter behaves this way, its distribution in the early universe wouldn't have been smooth. Clumps of it could have ignited whole clusters of dark stars, creating unseen powerhouses that heated the cosmos long before nuclear fusion took over. The hunt for these ghosts is already underway. Astronomers scour JWST data for spectra that match dark star predictions' specific ratios of helium and hydrogen, or unexpected infrared signatures. Other teams model how dark stars would interact with their surroundings, searching for traces in the cosmic microwave background. Even gravitational wave detectors might one day catch the echoes of their collapse, a telltale ripple in spacetime from the birth of a primordial black hole. What's astonishing is how much these theoretical objects blur the line between known and unknown. They force us to confront the possibility that the first light in the universe didn't come from stars as we know them, but from something stranger, something woven from the fabric of darkness itself. And if dark stars really did exist, their legacy wouldn't just belong to astrophysics. It would be a living one, echoing in every galaxy, every black hole, even the unseen matter that still binds the cosmos together. Supermassive black holes aren't just cosmic oddities, they're the universe's ultimate timekeepers, carrying secrets from an era when galaxies were nothing more than swirling dreams in the dark. The sheer scale of these gravitational monsters defies imagination. Take Sagittarius at the Milky Way's heart. Though relatively modest at 4 million solar masses, it's dwarfed by true titans like the black hole powering quasar Ton 618, weighing in at a staggering 66 billion suns. But here's the puzzle that keeps astrophysicists awake. How did such inconceivably massive objects emerge so quickly after the Big Bang? The answer might lie in seeds, cosmic embryos far heavier than any modern star could produce. When population 3 stars died, some may have collapsed directly into black holes hundreds of times the Sun's mass, skipping the supernova stage entirely. These wouldn't be the delicate remnants we see today, but primal beasts packing the raw material to grow exponentially. Picture a newborn black hole plunging into a dense gas cloud, consuming matter so rapidly it doubles in size every few million years, a feeding frenzy that could birth a quasar before the universe turned 1 billion. Yet even that might not explain the speed. Enter dark stars again, those theoretical giants powered by annihilating dark matter. If they existed, their collapse could create black hole seeds thousands of times more massive from the outset, jump-starting the growth process. Recent simulations show these exotic seeds wouldn't just sit quietly. Their immense gravity would distort nearby space, funneling gas toward them in raging torrents. Within cosmic moments, mere hundreds of millions of years, they'd balloon into the supermassive monsters we detect as quasars in the early universe, but black holes didn't grow in isolation. Their violent adolescence sculpted entire galaxies. Quasar jets moving at nearly light speed acted like cosmic blowtorches, heating surrounding gas so intensely it couldn't cool to form stars. This feedback mechanism became a universal regulator. Too much black hole activity, and star formation shuts down; too little, and galaxies overgrow. The result: the elegant balance we see today, where most galaxies host black holes precisely proportional to their bulges. It's as if the universe itself imposed a gravitational speed limit, with supermassive black holes as the enforcers. Now we're finding clues that these ancient giants might speak to us through more than light. When two supermassive black holes spiral toward collision, they warp spacetime itself, sending out ripples called gravitational waves. Unlike the high-frequency waves LIGO detects from stellar mass mergers, these low-frequency vibrations could span light years between peaks, a bass note resonating across cosmic time. Current pulsar timing arrays are listening for this hum, the combined chorus of every supermassive black hole merger in history. If detected, it wouldn't just confirm their collisions, it could reveal populations of primordial black holes we've never seen, tracing their growth from the universe's first moments. The most thrilling possibility: some supermassive black holes might predate their own galaxies. Observations of quasars in the cosmic dawn show them already fully formed while their host galaxies are still nebulous clouds. This reversal of our expected timeline, black holes building galaxies rather than the other way around, could mean these gravitational titans were the architects all along, their overwhelming gravity gathering the gas that would eventually spark into stars. We may have gotten the story backward for decades, mistaking the sculptor for the sculpture. Every discovery peels back another layer of this mystery, revealing a universe where darkness shaped light, where invisible behemoths guided the birth of everything we see. And as our telescopes grow sharper, we're not just studying black holes, we're decoding the universe's original blueprint, written in gravity's own hand. Gravitational waves are more than just cosmic ripples, they're ancient messengers carrying news from construction sites where the universe built its grandest structures. Picture spacetime as a vast pond, and colliding black holes as stones flung into its surface. The waves they create aren't mere disturbances, they're encrypted bulletins detailing events that shaped reality billions of years ago. When LIGO first detected these tremors in 2015, it wasn't just observing a black hole merger, it was eavesdropping on the aftermath of stellar architects at work. Some of these collisions defy expectations. Take JWST, a gravitational wave signal from two black holes merging into 185 solar masses, a size theory claimed shouldn't exist. One explanation: these could be primordial black holes, formed not from dying stars but from the seething density of the early universe. Their sheer mass suggests they bypassed normal stellar evolution entirely, growing through mergers in cosmic backwaters where galaxies hadn't yet formed. If confirmed, each detection would be like finding a lost page from the universe's blueprint, revealing construction methods we never imagined. The future of gravitational wave astronomy promises even deeper revelations. The upcoming LISA mission, a space-based detector slated for the 2030s, will hunt for low-frequency waves impossible to catch on Earth. These could include the death throes of supermassive black hole pairs, events so colossal they'd make LIGO detections seem like whispers. More tantalizing still, LISA might uncover cosmic strings, hypothetical defects in spacetime left over from the Big Bang. These ultra-dense filaments would vibrate like guitar strings, producing gravitational waves with a unique fingerprint. Finding them would prove the universe underwent phase transitions in its infancy, like water freezing into ice with cracks between the crystals. Every chirp, every ripple in the data carries implications for life itself. The heaviest elements, gold, platinum, uranium, are forged in neutron star collisions, events gravitational wave observatories now routinely detect. Without these cataclysmic mergers, Earth's core might lack the radioactive elements that keep it molten, depriving our planet of its protective magnetic field. Even the distribution of galaxies could trace back to gravitational wave sources, their energy nudging matter into the filaments and voids we see today. What's astonishing is how recently we gained this new sense. For centuries, astronomy relied on light alone. Now we're feeling the universe's vibrations too, listening to the groans of colliding black holes, the shudders of neutron stars, perhaps soon the birth pangs of spacetime itself. Each signal adds an instrument to our cosmic orchestra, tuning our understanding of how everything from atoms to galaxies came to be, and the composition. It's still being written, one gravitational echo at a time. Every atom in your body that isn't hydrogen carries the signature of stellar violence. Carbon in your cells, oxygen in your breath, iron in your blood, these weren't forged in laboratories or cooked up in Earth's crust. They were born in the hearts of dying stars, blasted across the cosmos in explosions so powerful they lit up entire galaxies. The universe started with just hydrogen and helium, the simplest elements. Everything heavier, every ingredient for planets, oceans, and life itself was crafted in stellar furnaces and scattered by cataclysms we're only beginning to understand. Take carbon, the backbone of organic chemistry. In stars like our Sun, carbon forms slowly through nuclear fusion, a byproduct of hydrogen burning, but the carbon that seeded our solar system likely came from somewhere far more dramatic, asymptotic giant branch stars, elderly suns that puff up like cosmic bellows in their final years. These dying giants blow carbon-rich winds into space, dusting surrounding nebulae with the stuff of life, yet even they're not the whole story. When massive stars go supernova, shockwaves rip through their outer layers, creating conditions so extreme they forge elements like silicon and sulfur in seconds. These metals don't just linger near the explosion, they hitch rides on shockwaves, traveling light years until they're captured by new clouds of gas. Oxygen, essential for water and respiration, tells an even wilder tale. Most of it comes not from gentle stellar winds, but from supernovas so violent they briefly outshine their host galaxies. When a star 20 times heavier than our Sun explodes, its core collapses into a neutron star, while the outer layers detonate at nearly 10% the speed of light. In that maelstrom, oxygen atoms fuse by the trillions, then get flung into the void. Some of that oxygen eventually found its way to Earth, dissolved in primordial oceans where the first microbes learned to harness its power. Iron, though, is where the story takes a darker turn. Unlike lighter elements, iron marks the end of a star's energy production. It's the ash left when nuclear fusion can no longer sustain the fight against gravity. In massive stars, iron accumulates in the core like a ticking time bomb. When enough builds up, the star's heart collapses in milliseconds, triggering a supernova so powerful it can briefly outshine a billion suns. That explosion doesn't just disperse iron, it creates even heavier elements like gold and uranium in the process. The gold in your wedding ring, it was likely forged in the neutron-rich debris of two colliding neutron stars, an event so rare and energetic it's detectable across the universe as a gravitational wave chirp followed by a fiery afterglow. But here's the twist, these elements didn't just drift aimlessly. Hypernova, supernova on steroids acted like cosmic shotguns, blasting heavy metals farther and faster than ordinary explosions could. Their intense gamma-ray bursts ionized gas clouds light years away, compressing them until they collapsed into new stars and planets. Some scientists believe a nearby hypernova might have even given our solar nebula the nudge it needed to collapse, setting the stage for Earth's formation. Without that push, the Sun and its planets might never have coalesced at all. Astronomers trace this elemental genealogy through starlight itself. Every element absorbs and emits light at specific wavelengths, creating barcode-like patterns in a star's spectrum. By analyzing these lines, researchers can read a star's composition like a cosmic ancestry report. Metal-poor stars, like those in the Milky Way's outer halo, carry the sparse chemistry of the early universe. Younger stars enriched by generations of supernova show heavier element signatures, proof of the universe's ongoing alchemy. Even meteorites, those ancient space rocks that fall to Earth, contain microscopic grains older than the Sun, each one a time capsule from the stellar factories that built our solar system. This isn't just history, it's a living process. Right now, in distant nebulas, new stars are forming from ashes of the dead. Their planets will inherit atoms forged in explosions we haven't even witnessed yet. And someday, long after our sun fades, its own remnants will join the cycle, seeding future worlds with the raw materials for whatever comes next. The universe doesn't just create elements, it recycles them, weaving an unbroken chain from the first stars to the last. Stellar archaeology transforms the night sky into an open history book, one where elements act as ink and stars are the pages. Take Iso 7-5240, a star so ancient its iron content is 1,000,000 times lower than our sun's. This isn't just a celestial relic, it's a forensic snapshot of the universe's first supernova. When astronomers analyze its spectrum, they're not seeing random element ratios but precise chemical fingerprints, evidence of hypernova explosions that blasted heavy metals into primordial gas clouds. The absence of certain elements like zinc suggests these early detonations were asymmetric, their shockwaves ejecting material in powerful jets rather than uniform shells. The most revealing clues come from stars with bizarre neutron capture elements. In ordinary supernova, these heavy metals form slowly, like bread rising over hours. But stars like BD plus 4449-3 show traces of rapid neutron capture elements, forged in seconds during events like neutron star collisions. The kicker: this star is nearly as old as the universe itself. Its existence implies that population 3 stars didn't just die in isolation. Their remnants must have merged cataclysmically, scattering gold and platinum across the cosmos while galaxies were still taking shape. Modern surveys like the Pristine project use narrowband filters to hunt these time capsules, targeting the oldest, most chemically pristine stars in our galactic halo. Their discoveries are rewriting stellar evolution timelines. One star in Sculptor, a dwarf galaxy orbiting the Milky Way, contained carbon but almost no iron, a signature suggesting it formed from gas enriched by a single, faint supernova rather than multiple explosions. This changes the game. Some first-generation stars may have died quieter deaths, their subtle chemical whispers preserved in stars we once overlooked. Now imagine switching perspectives from the delicate chemistry of ancient stars to the universe's most violent outbursts. Gamma-ray bursts are the cosmic equivalent of air raid sirens, screaming across the electromagnetic spectrum with energies that dwarf supernova. Lasting from milliseconds to minutes, these beams of concentrated fury represent the birth cries of black holes or the collision of neutron stars. When satellites detect a burst, they're capturing light that's traveled for billions of years, carrying news of celestial catastrophes from the universe's youth. And just like stellar archaeology decodes the past through chemistry, gamma-ray bursts offer a different kind of time travel, one written in photons of pure annihilation. Gamma-ray bursts are the universe's ultimate fireworks, spectacular finales so powerful they can outshine every star in the observable cosmos combined, if only for a few fleeting seconds. These explosions come in 2 flavors, each more extreme than the last. Short bursts, lasting less than 2 seconds, are thought to arise from neutron star collisions, the same events that forge gold and platinum. But the real showstoppers are the long bursts. lasting minutes or even hours, which signal the death of massive stars in hypernova so violent they resemble supernova pumped with cosmic steroids. When a star dozens of times heavier than our Sun exhausts its fuel, its core doesn't just collapse, it implodes into a black hole with such force that twin jets of plasma pierce through the star at nearly light speed. These jets, hotter than a trillion suns and packed with gamma rays, blast into space like celestial blowtorches, and if Earth happens to lie in their path, the results could be apocalyptic. What makes GRBs truly remarkable isn't just their energy, it's their reach. The most distant burst ever recorded, JWST 90429, detonated when the universe was barely 500 million years old. Its light traveled for over 13 billion years before meeting human detectors, carrying whispers from an era when galaxies were still taking shape. That beam, now fossilized into radio waves, offers a rare glimpse into the early cosmos, illuminating gas clouds and proto-galaxies like a flashlight piercing fog. Astronomers call this phenomenon an afterglow, and it's more than just pretty radiation. By analyzing how these afterglows interact with intervening matter, scientists can map the universe's chemical evolution. GRBs act as cosmic backlights, revealing elements like magnesium and silicon in galaxies too distant to study directly, yet these bursts aren't just celestial history, they're existential threats. A GRB within a few thousand light-years could strip Earth's ozone layer, bathing the surface in deadly ultraviolet radiation. Some researchers suspect a nearby burst might have triggered the Ordovician mass extinction 450 million years ago, wiping out 85% of marine species. The telltale signature, a sudden spike in radiation-sensitive isotopes in ancient rock layers, paired with fossil evidence of plankton species that thrived in shallow water suddenly vanishing. Even today, satellites detect a GRB somewhere in the universe roughly once per day, a reminder that these explosions aren't relics, they're ongoing cosmic artillery. But GRBs also played a paradoxical role in making life possible. During the Epoch of Reionization, when the first stars and quasars were burning away the universe's hydrogen fog, gamma-ray bursts may have acted as supplemental torches. Their intense radiation could have helped ionize pockets of gas too distant from quasars to be cleared otherwise, effectively widening the tunnels through which light could travel. Recent simulations suggest that without GRBs, certain regions of the early cosmos might have remained opaque for hundreds of millions of years longer, delaying the formation of galaxies in those areas. In this way, the universe's most destructive forces were also midwives to its large-scale structure. The afterglows tell another story, one of elemental alchemy. When a GRB's jet slams into surrounding gas, the shockwave creates conditions so extreme they forge elements like titanium and nickel in seconds. These metals don't just linger near the explosion, they're accelerated to relativistic speeds, becoming cosmic bullets that seed future star-forming regions. Some astronomers speculate that the iron in your blood might trace its lineage not just to ordinary supernova, but to hypernova-driven GRBs that peppered the early universe with heavy elements. Now, as we piece together the GRB puzzle, new mysteries emerge. Why do some dying stars produce these jets while others don't? How did early stars, composed of pure hydrogen and helium, manage to trigger GRBs without metals to catalyze their collapse? The answers might lie in population Roman 3 stars, those first, gigantic stellar pioneers whose deaths could have been even more violent than predicted. Upcoming observatories like the Vera Rubin telescope aim to catch these bursts in their infancy, watching as their light creeps across galaxies like a shockwave in slow motion. Each detection isn't just data, it's a postcard from the edge of space-time, sent by the universe's most reckless architects. The Epoch of Reionization wasn't just a phase, it was the universe's great awakening, the moment it shook off the last remnants of its primordial slumber. Picture a cosmos suffocated by darkness, where hydrogen gas hung thick like a billion-year fog, swallowing light whole. Then, almost imperceptibly at first, pinpricks of ultraviolet radiation began piercing through. These weren't random flickers, they were the birth cries of quasars and the first stars, their relentless radiation stripping electrons from hydrogen atoms in a cosmic chain reaction that would eventually illuminate the entire universe. What made this transformation possible? The answer lies in those ancient stellar architects we've been following. Population 3 stars. Though they lived fast and died young, their ultraviolet photons acted like cosmic scalpels, carving ionized bubbles in the hydrogen fog around them. As more stars ignited, these bubbles expanded and merged, creating tunnels of transparency through which light could finally travel freely. Quasars amplified the effect, their searing radiation reaching far beyond individual galaxies, like lighthouses cutting through a global storm. But reionization wasn't uniform. JWST recent deep field images reveal a patchwork cosmos, some regions ionized early, others stubbornly clinging to neutrality. This unevenness is a goldmine for astronomers. By studying the distribution of these ionized bubbles, they can reconstruct the timeline of reionization, identifying which celestial phenomena drove the process and when. One startling discovery: the bubbles grew faster than models predicted, suggesting hypernova and gamma-ray bursts might have played unsung roles, their shockwaves compressing gas and triggering secondary waves of star formation. The shadows of this epoch linger in the cosmic microwave background, the afterglow of the Big Bang itself. Tiny fluctuations in this ancient light bear scars from reionization's final stages, like fossils preserved in amber. When the Planck satellite mapped these imperfections, it revealed something profound. Reionization likely peaked around 550 million years after the Big Bang, but began much earlier, seeded by ultraviolet pioneers in the cosmic dark. Perhaps the most haunting legacy of reionization is its influence on galaxy formation. Those early ionized bubbles didn't just clear space, they set the stage for cosmic structure. Gas that had been too hot and diffused to collapse suddenly found itself able to cool, fragment, and birth new generations of stars. The universe didn't just become transparent, it became fertile. And the architects behind this transformation, they're long gone, their light faded into the infrared background, but their fingerprints are everywhere in the distribution of galaxies, the chemistry of intergalactic gas, even the fact that we can see the stars at all. Now, as JWST peers deeper into this era than ever before, we're not just observing history, we're witnessing the moment the universe turned the lights on. And every new image carries clues about how darkness became light, how chaos became structure, and how a few fleeting stellar giants ignited the cosmos we call home. Lyman alpha forests are the universe's oldest ghost stories, faint whispers of hydrogen clouds, imprinted on light that's traveled for billions of years. When quasars beam their intense radiation across the cosmos, their light doesn't arrive untouched. Countless clouds of neutral hydrogen, strung along the line of sight like beads on a string, absorb specific wavelengths, leaving behind a barcode of dark lines in the quasar's spectrum. To the untrained eye, it might look like noise, but to astronomers, these absorption lines are a Rosetta Stone, decoding the distribution of matter during the universe's most transformative era. What makes these fora so revealing is their sheer density. A single quasar spectrum can contain hundreds of absorption lines, each one a snapshot of hydrogen at a different distance and, therefore, a different cosmic epoch. The closer the lines are packed, the denser the gas was at that point in space and time. By mapping these patterns across thousands of quasars, scientists reconstruct a 3D tomographic image of the early universe, unveiling its filamentary skeleton. Voids where lines are sparse trace the locations of future galaxy clusters. Dense thickets mark the protogalactic clouds that would one day ignite into stars. It's like reading the growth rings of a tree, but instead of years, each layer reveals millions of years of cosmic evolution. Temperature tells another story. The width of each absorption line betrays the hydrogen cloud's thermal state. Broader lines mean hotter gas, likely heated by ultraviolet radiation from early stars or quasars. Recent analysis of quasars like ULA's J12+0641 shows something startling: patches of gas that were already scorching hot when the universe was barely 800 million years old. This suggests reionization wasn't a gentle dawn, but a series of violent flashpoints, where bubbles of ionized gas erupted unpredictably, like fireworks in a midnight sky. The most tantalizing clues come from anomalies, regions where the forest suddenly thins or vanishes. These could be the footprints of hypernova, whose shockwaves blew colossal cavities in the intergalactic medium. Others might mark the paths of quasar jets, their radiation bulldozing hydrogen out of the way. Each gap is a fossilized echo of ancient stellar catastrophes, events so powerful they rearrange the cosmos on scales we're only beginning to fathom. But the true magic of Lyman alpha forests lies in their duality. They're not just relics, they're dynamic records. As light from newer quasars passes through older hydrogen, it captures how structures evolved over billions of years. Compare spectra from quasars at different distances, and you're watching the universe grow up in time-lapse, seeing filaments condense, voids expand, and the cosmic web take shape. It's as if each quasar is a flashlight shone through layers of cosmic sediment, illuminating the strata of spacetime itself. Now hidden in the subtlest variations of these forests might be clues to an even earlier epoch: cosmic inflation, the universe's exponential expansion in its first fraction of a second. The distribution of hydrogen clouds at the largest scales could carry imprints of quantum fluctuations stretched to cosmic proportions, a fingerprint of the forces that set the entire cosmic web in motion. To read them, though, we'll need to dig deeper past the forests, past the quasars, into the primordial whispers etched in the afterglow of creation itself. Cosmic inflation wasn't just an expansion, it was the universe's first and most dramatic construction project, stretching spacetime itself faster than light in fractions of a second. Picture a speck smaller than a proton unfurling into a volume trillions of times larger, smoothing and flattening the cosmos like dough under a rolling pin. Yet hidden in this exponential growth were quantum seeds, tiny fluctuations that would one day become galaxies. These weren't random wrinkles, they were the universe's first blueprints, imprinted when inflation magnified subatomic vibrations into cosmic scale density variations. Without this primordial stretch, the cosmos might have remained featureless, devoid of the gravitational anchors that later sculpted stars and planets. What's astonishing is how precise these fluctuations had to be. Too weak, and matter would never have clumped into galaxies. Too strong, and the universe would have collapsed back into black holes long before life could emerge. The Goldilocks perfection of inflation's quantum whispers hints at something deeper, a fundamental balance between chaos and order written into the laws of physics itself. Some theories even suggest these fluctuations might have birthed primordial black holes, those hypothetical dark matter candidates, as dense regions collapsed under their own gravity during inflation's final moments. If true, these ancient black holes could be hiding in plain sight today, their collective gravity shaping galaxies while remaining nearly invisible. The clearest evidence for inflation lies in the cosmic microwave background's eerie uniformity. No matter which direction we look, this relic radiation varies by less than 1 part in 100,000, a smoothness impossible without spacetime's ultra-rapid stretching. Yet the CMB also holds tiny temperature variations, freeze frames of those quantum seeds grown cosmic. Planck satellite measurements reveal their pattern matches inflation's predictions with uncanny precision, like finding a fossil with perfectly preserved DNA. But the smoking gun, the telltale ripple of gravitational waves from inflation itself, remains elusive. Future observatories like the LightBird satellite aim to hunt these waves in the CMB's polarization, a signal that would confirm inflation's ultra-energetic origins. Inflation's legacy isn't just in the past, it set the tempo for everything that followed, determining how quickly galaxies formed, how dark matter clustered, even how vacuum energy might one day tear spacetime apart. Some models suggest inflation never truly ended, with distant regions of the universe still inflating eternally, spawning infinite bubble universes beyond our horizon. Others propose that the same quantum fields driving inflation might have later triggered reheating, filling the universe with the hot plasma that birthed the first particles. The most profound implication, without inflation's quantum fingerprints, those population 3 stars might never have ignited. The densest fluctuations became the first gravitational wells, collecting hydrogen and helium into protogalaxies where stellar giants could take shape. In this way, inflation didn't just prepare the stage for cosmic architects, it handed them their tools. And as we peel back layers of cosmic history, we're not just tracing the universe's evolution. We're deciphering the opening lines of a story written in spacetime's own hand, one where the tiniest quantum flickers gave rise to everything from black holes to beating hearts. Now, as we stand at the edge of comprehension, peering into the unknown, one question remains: what other blueprints lie hidden in the cosmic dark? The cosmos loves its mysteries, and even with all we've uncovered, the blueprints of the universe still hold pages we can't yet read. Take reionization, that pivotal era when the universe woke from its dark age. We know the first stars and quasars lit the match, but was it a gradual dawn or a series of sudden flashes? Some regions of space ionized suspiciously early, while others clung to darkness like cosmic holdouts. The latest James Webb observations only deepen the puzzle, revealing galaxies that appear too mature, too soon, their starlight suggesting reionization might have been a patchwork quilt stitched together by forces we're only beginning to trace. Then there's the enigma of primordial black holes. These hypothetical relics from the universe's first second could solve 2 mysteries at once: dark matter and the rapid growth of supermassive black holes. But after decades of searching, we've yet to catch one in the act. Microlensing surveys watch for their subtle gravitational tugs. Gamma-ray telescopes hunt for their theoretical evaporation sparks. Every null result tightens the constraints, yet the possibility lingers like a shadow at the edge of our models. If they're out there, hiding in the voids between galaxies or clustered in dark halos, their discovery wouldn't just fill a gap, it would rewrite cosmic history. Speaking of black holes, their supermassive cousins defy logic. Quasars like J1342 plus 928, blazing when the universe was barely 700 million years old, weigh in at billions of solar masses. Even if they grew at the maximum theoretical rate, feasting on gas non-stop, the math barely adds up. Could direct collapse black holes, monsters born from imploding gas clouds, skipping the star stage entirely, be the missing link? Or does dark matter's hidden physics accelerate their growth in ways we haven't imagined? The upcoming LISA mission might hear the answer in gravitational waves from mergers that happened when the cosmos was in diapers, but the anomalies don't stop there. The Hubble tension, a stubborn discrepancy in how fast the universe is expanding, hints that something fundamental is missing from our playbook. Is dark energy evolving? Are there unseen particles tweaking gravity on cosmic scales? Meanwhile, dark flow, the peculiar drift of galaxy clusters toward an invisible attractor, suggests structures beyond our observable horizon might be pulling strings we can't see. And let's not forget dark energy itself, that enigmatic force accelerating the expansion of space. Is it Einstein's cosmological constant, or something far stranger, a field that fluctuates or strengthens over time? These aren't just gaps in knowledge, they're cracks in the foundation of modern cosmology, and they're growing wider with every new observation. But here's the thrilling part: each unsolved mystery is a doorway, not a dead end. The Euclid telescope is already mapping dark matter's web in 3D, searching for whispers of modified gravity. The Vera Rubin Observatory will scan the skies for transient phenomena that could reveal hidden physics. And next-generation gravitational wave detectors might finally catch the chirp of a primordial black hole merger, or the hum of cosmic strings vibrating from the universe's birth. The unknown architects aren't just relics of the past, they're active collaborators in the cosmos' unfolding story, and as we turn our telescopes toward the shadows, we're not just hunting for answers. We're learning how to ask better questions. The next chapter in our cosmic detective story is already unfolding, with telescopes so advanced they border on time machines. The Nancy Grace Roman Space Telescope, launching in the mid-2020s, carries a mission that would make its namesake proud: to map dark matter's invisible hand on a scale never before attempted. Using a technique called gravitational lensing, Roman will detect how dark matter distorts the light from millions of galaxies, revealing its fingerprint across 11 billion years of cosmic history. But here's the revolutionary part: by combining this data with measurements of galaxy shapes and positions, scientists will reconstruct how dark matter guided the growth of structure from the era of population, 3 stars, to today. It's like unrolling a cosmic scroll that's been tightly wound since the beginning, finally reading the instructions dark matter wrote in gravity's own language. Meanwhile, the square-kilometer array SKA prepares to listen to the universe's oldest whispers. This sprawling network of radio antennas across 2 continents will be sensitive enough to detect the faint hydrogen signals from the first stars as they ignited. Imagine catching the static-filled birth cries of stars that died 13 billion years ago, their radio waves stretched by cosmic expansion into faint murmurs. SKA won't just hear these pioneers, it will map the cosmic web in hydrogen, tracing how filaments of gas funneled matter into galaxies. There's even a chance it could pick up hypernova remnants, expanding bubbles of metal-rich debris that should leave distinct imprints in the radio spectrum. Each detection would be a fossilized echo of those first catastrophic explosions. Then there's Athena, the advanced telescope for high-energy astrophysics, poised to launch in the 2030s with X-ray vision sharp enough to dissect supermassive black holes in their infancy. While Roman maps dark matter and SKA listens for ancient hydrogen, Athena will study the violent adolescence of quasars, watching how their X-ray emissions heated surrounding gas during reionization. Its spectrometers can measure the temperature and motion of intergalactic plasma to a precision once unimaginable, effectively taking the cosmic web's temperature. One of its boldest goals, to catch a direct collapse black hole in the act of formation, a hypothetical monster born when a gas cloud bypasses starlight and implodes directly into a black hole. Such a discovery would rewrite our understanding of how the universe built its gravitational anchors. What ties these missions together is their shared ambition to decode the universe's hidden instruction manual. Roman's dark matter maps might reveal how primordial black holes, if they exist clustered into invisible scaffolds, SKA could uncover whether population 3 stars died solo or in coordinated bursts that reshaped entire regions of space. Athena may prove that supermassive black holes didn't grow from stars at all, but emerged fully formed from the chaos of the early cosmos. Together, they form an interdisciplinary toolkit to interrogate the past with forensic precision. We're standing at the threshold of a new era, one where ancient history means events from the universe's first billion years, and discovery involves reconstructing processes that shaped everything from galactic superclusters to the iron in our blood. These missions don't just aim to fill gaps in our knowledge, they're designed to surprise us, to expose the flaws in our current theories, and to reveal cosmic architects we haven't even dreamed of yet. The golden age of cosmology isn't behind us. It's being built now in clean rooms and control centers by scientists and engineers who are, in their own way, becoming architects of understanding. And as these telescopes turn their eyes and ears to the sky, they won't just be observing the universe, they'll be completing a story 13 billion years in the telling, one where humanity finally meets the builders. Humanity's cosmic connection runs deeper than poetry. It's written in the very elements that make our bodies and our world. Every time you take a breath, you inhale oxygen atoms forged in the heart of a supernova. The gold in a wedding ring, it was likely born in the collision of two neutron stars over 4 billion years ago, their violent embrace scattering precious metals across the galaxy until some found their way to Earth. Even the calcium that strengthens your bones was once stellar ash, ejected by a dying star that exploded before our solar system formed. These aren't metaphors, they are forensic facts confirmed by spectroscopy and particle physics. Consider carbon, the backbone of life. Most of it originated in asymptotic giant branch stars, ancient, swollen giants that blew carbon-rich winds into space like cosmic gardeners scattering seeds. When our solar system condensed from a nebula 5 billion years ago, those carbon atoms became the basis of every organic molecule on Earth. The same process repeats across the galaxy. On Saturn's moon Titan, rivers of methane flow beneath orange hydrocarbon skies. In distant nebulae, astronomers detect sugars and amino acids, prebiotic molecules built from stellar ingredients. The universe isn't just hospitable to life, it's actively manufacturing its raw materials, but our connection isn't merely chemical. The human brain, with its 86 billion neurons, might be the most complex structure we know of in the cosmos. Those neurons fire using sodium and potassium ions, elements created exclusively in supernova. Your ability to ponder the stars, to feel awe at their beauty, depends on stellar explosions that occurred billions of years ago. In a very real sense, the universe evolved stars so that one day they could evolve creatures capable of understanding them. This reciprocity extends to our tools. When the James Webb Space Telescope peers back at the era of the first galaxies, it does so with a mirror coated in gold, a metal born in stellar cataclysms. Our technology is literally made from stardust, allowing us to decode the very processes that created it. Even the silicon in computer chips traces its lineage to oxygen-burning shells of massive stars, while the uranium powering nuclear reactors was forged in the unimaginable pressures of colliding neutron stars. The most humbling realization: we're not passive observers. By studying ancient stellar phenomena, we've uncovered laws of physics that let us harness energy, cure diseases, and explore space. The same nuclear fusion that powers stars now lights our cities through experimental reactors. Particle accelerators recreate conditions from the first microseconds after the Big Bang. In trying to understand the universe, we've learned to manipulate its fundamental forces, a feedback loop where cosmic history enables human progress. Yet for all our knowledge, mysteries remain. Why did these specific stellar events conspire to create a planet so perfectly suited for life? Why does the human brain resonate so deeply with the beauty of nebulae and galaxies? Perhaps it's because recognizing our kinship with the cosmos isn't just science, it's a homecoming. Every atom in your hand once traveled through interstellar space, rode shockwaves from supernova, and circled in protoplanetary disks before becoming part of you. You're not just in the universe, you are the universe, a sentient collection of ancient stardust discovering its own origins. As we recast the key takeaways, remember this isn't just astronomy, it's genealogy on the grandest scale. The story of the cosmos isn't locked in distant galaxies, it's written in your bones, your breath, and the electricity sparking through your thoughts. And with every scientific revelation, we don't just uncover the past, we glimpse our shared future in the stars. The universe is an epic still being written, a story where the ink is stardust and the authors are forces beyond human scale. Those first population 3 stars weren't just fiery pioneers, they were alchemists, turning hydrogen and helium into the elements that would build planets and people. The hypernova that shattered them weren't mere explosions, they were cosmic forges hammering gold and uranium into existence. Quasars weren't just beacons in the dark, they were painters, etching transparency into the universe with strokes of ultraviolet light. And those hypothetical primordial black holes, they might be the unseen masons, their gravity laying the foundations for galaxies before the first stars even flickered to life. What's astonishing isn't just their individual roles, it's how they collaborated across billions of years. A hypernova's shockwave might have compressed a gas cloud, birthing stars whose radiation later cleared a path for quasar light. A primordial black hole's gravity could have steered that same cloud into a filament of the cosmic web, where it merged with others to form a galaxy. The universe doesn't operate in isolation, it's a symphony where each note resonates through eternity. Now we're the witnesses to that symphony. With tools like JWST and LIGO, we're not just observing history, we're reverse engineering it, peeling back layers of time to uncover how these architects work. And every discovery upends old certainties, quasars shining too soon, galaxies clumping too fast, elements appearing where they shouldn't. These aren't flaws in the data, they're clues that the cosmos is more creative, more improvisational than our textbooks ever allowed. But here's the most humbling truth, you're holding evidence of their work right now. The device you're watching this on contains silicon forged in a dying star's core. The oxygen in your lungs was once stellar ash. Even the electricity powering your screen owes its existence to forces set in motion during the universe's first seconds. We're not separate from the cosmos, we're its living, breathing archive. So the next time you look up at the night sky, remember, you're not just seeing distant lights. You're seeing the legacy of giants, the echoes of explosions that shaped space-time itself, and somewhere out there, in the glow of a quasar or the whisper of a gravitational wave, the next chapter is being written, one will help unravel. The architects may be gone, but their blueprint, it's still unfolding, and we're here to read it. The cosmos hums with the echoes of its architects, those titanic ancient forces that sculpted the void into galaxies, stars, and the very atoms that compose our world. Their work isn't confined to some distant past, it's alive in the way galaxies spin, in the light that journeys billions of years to reach our telescopes, even in the pulse of your own heartbeat. Every time we peer into the night sky, we're not just observers, we're participants in a story 13 billion years in the telling, standing shoulder to shoulder with the remnants of those first celestial pioneers. Consider the Hubble Deep Field, that iconic image where a patch of sky no larger than a grain of sand held thousands of galaxies. Each one is a testament to those forgotten builders' population, 3 stars whose explosive death seeded the cosmos with heavy elements, quasars whose radiation carved transparent pathways through the primordial fog, and dark matter's invisible hands, which gathered gas into the first gravitational wells. These weren't random acts of creation, they were the universe learning how to build itself, refining its techniques over eons until spirals like the Milky Way could cradle solar systems and planets ripe for life. Yet the architect's legacy isn't frozen in time. Right now, in the turbulent hearts of starburst galaxies, new generations of stars are being forged from the ashes of their ancestors. Supermassive black holes, dormant for millennia, can awaken to reshape their galaxies with jets of plasma hotter than 1 trillion suns. Even our own solar system drifts through a cloud of stardust debris from explosions that occurred long before Earth formed. The universe isn't some static museum exhibit, It's a dynamic construction zone, with blueprints written in the language of gravity, light, and quantum fluctuations. What's thrilling is how much we've yet to uncover. The James Webb Space Telescope's infrared eyes are revealing galaxies so ancient they shouldn't exist, challenging our timelines of cosmic evolution. Gravitational wave detectors are tuning into the murmurs of black hole mergers, events so violent they warp spacetime itself, and lurking in the data might be the answers to questions we haven't even thought to ask yet, like whether dark stars once illuminated the cosmos, or if primordial black holes truly are the missing pieces of the dark matter puzzle. This isn't just about satisfying curiosity, it's about tracing our lineage. The calcium in your teeth, the iron in your blood, the very device you're using to watch this video, all were crafted in the hearts of dying stars. We're not just studying the universe, we're made from it, bound to it in the most intimate way imaginable, and as we unlock these secrets, we're not just looking backward. We're preparing for a future where humanity might one day journey beyond our solar system, guided by the same cosmic principles those first architects set in motion. So the next time you step outside on a clear night, remember, you're standing in a living cathedral built by forces older than time. Their work is etched into the constellations, whispered in the light of distant quasars, even written in the DNA that shapes your existence. The universe's greatest stories are still being told, and with every discovery, we're adding our own verse. If this journey through space and time has sparked your imagination, join us in the conversation below. Hit like, subscribe, and let's keep unraveling the cosmos together, because the next chapter, it's ours to